Hello, it's my pleasure to talk about polynomial interpolation. Okay, polynomial interpolation, we're going to give a good example, and we're going to use the Newton style that's shown in the book. So remember, for your polynomials, there's a couple of different ways to do it. I like to use n plus 1 coefficients that are given in ascending order for an nth degree polynomial. So that's how I do it. And, I've shown you my Horner function. So the Horner function, I provide the coefficients in ascending order, and then the x that I want the polynomial to be evaluated. That's how I do it. If I were to use the MATLAB polynomial evaluation function, the polyval, I'd have to flip reverse the order of the coefficients because MATLAB wants the coefficients in descending order, and they will provide n coefficients for an n minus 1 degree polynomial. So a little bit weird. So it's okay as long as you know which way it is. So for there, if you have their coefficients, you'd have to flip them in order to use my Horner, or you could just use their polyval straight up. So watch out how the coefficients might start with a 0 in my case, because that's my constant. And then my coefficients, the a1 will go with the linear, the a2 will go with the square, and then the an goes with the nth degree x. And then their coefficients will start from 1, and 1 being the highest, and then the coefficients will increase, but the first coefficient will go with the highest degree x. So anyway, I just thought it would serve you well just to watch out for how do you represent these polynomials. Okay, so here's what we're going to do. We're going to take some data. We're going to focus on the temperature here being like an x value, and then we're going to focus on this density here corresponding to sort of a y value. And we're not going to worry about the viscosity stuff here. We're going to focus on the first two columns, and we're going to try to look at some interpolation in there. And we're going to focus on 4 points that are sort of in the middle. And we're going to try to fit a cubic through those 4 points. So that's where we're going to steer today. Okay, but in general, the general idea is if you have 2 points that you're going to do a polynomial fit, well, you just have a line segment. So that's just a linear first order connecting those 2 points. If you have 3 points, then you can do a quadratic for that. And if you have 4 points, like I was just talking about, if you have 4 points, then you can put a cubic through those 4 points, and then you can interpolate to your heart's content in between the points. So just kind of the takeaway is you're going to take a group of n data points, and here we're talking 4, and a polynomial that would need n coefficients. That means that the polynomial degree will be 1 less. So for 4 points, we're going to end up putting a cubic through that. Okay, how do we do that? We're going to use Newton's interpolating polynomials. I just wanted to say that we wouldn't want to use a general regression or linear regression that we had studied earlier. This is not going to be very accurate because of the condition is going to be make it very, very sensitive to changes. So large condition values. So because of this, we're going to be using Newton's interpolating polynomials just like what's in the book. Okay, so here's our book example, and we're going to start with a 1 degree polynomial. We're going to start from the basics. So for linear interpolation, let's imagine that I'm looking at the points, the quote-unquote x points, the temperature points, the 50 and the 100. And associated with them, I've got the densities of 1.09 and 0.946. So temperature is in Celsius and density is kilograms per cubic meter. And I'm interested to see what the value 75 would be. So how interpolation would work. for a 1 degree polynomial, you would have the function at 50. So the function is going to be this column. The function is, what the y value is. So the f of x is y. So, kind of use these interchangeably. But I want to know what the f1, so that's the first degree polynomial value at x equals 75. Well, I'm going to take the f of 50, which is going to be 1.09, right? I'm going to take that, and I'm going to add to it the f at 100, which is 0.946, minus the f at 50, which is the 1.09. And I'm going to be dividing by the delta x, 100 minus 50, and that's going to establish that. The x is going to be 75, and the offset in x is going to be 50. So I'm coming from 50 going to 100. So that's why that 50 is there, and I'm marching from 50 towards this 75. This effectively is the slope here. Right, and I can't call this the a naught. This is a1, but I can't call this the a naught because there's a minus 50 that kind of gets shoved up over there. So the minus 50 times the slope that gets pulled over here. This is the a naught part. So that if you were kind of looking at how do I break up that polynomial with the constant term plus the linear term times x. And there's the linear term, which is the slope, times x. So this is how it kind of works out. But to be honest, this is a very convenient way, more convenient than kind of slogging through to see what the coefficients of the polynomial are. But you could do that if you wanted to. So this is a very convenient, and this is the Newton's method of doing the polynomial interpolation. So that's linear. Let's see if we can look at quadratic. So for quadratic, we're going to add the third point, which is 150. What you do is you maintain what you had for the linear part, and you just add another term to it, and that's it. That's it. So here's the other term, and it kind of gets a little bit broad here. It's almost a recursive type of thing. So I'm going to have this term that I'm adding. I'm going to have it almost looks like this. It's really just kind of a derivative. So that's a change in slope is what this is representing here. So I'm doing 150 minus 100, the f of 150 minus the f of 100 divided by 150 minus 100. So I'm looking at these two rows when I do that. I still have these values, right, that I had before. So now I'm adding in the f of 150, and that's going to make this part here be really kind of the slope between 100 and 150. That's what this is going to be. And this is going to be the slope that we had earlier between 50 and 100, right? And then you're going to be doing a difference in those slopes divided by the 150 minus the 50. So that's going to set up like a change in slope, and we're multiplying it by what we had before, x minus 50, and also an x minus 100. If you actually kind of think about what this has given us, there's going to be obviously a constant here because we know everything there, and you're going to have an x squared. You're going to have an x because you're going to have minus 50, and then you have a minus 100, minus 50x minus 100x. And then you're going to have minus 50 times a minus 100. So this is going to be a full quadratic polynomial. So it's going to effectively add to the a naught we had before, the a1 we had before, and then there's going to be an a2 for this. So every time we add a term with the Newton's method, it's very convenient to add these terms, by the way. But every time we add a term, we're actually increasing or changing all of the coefficients of our polynomial. Okay, what's the takeaway here? Well, we've added a term, and it's going to affect all of the earlier coefficients that we had. And it's every time we add a term, it's going to add a new It's going to add a new degree for our x, and it's also going to add a new coefficient for that polynomial. So the same thing's going to happen for the cubic, and it's really just easier to handle this by using the brackets of the Newton's method, like I'm going to show you now. Okay, so the bracket, so if it's linear, as we said, we're going to have we're going to have the f of the x1 of the very first point. So this is going from x1 to x2, right? So I'm just going to call that b1, bracket 1. And then I'm going to call that slope, I'm going to call that b2, or bracket 2. And then the x value comes in, and here that you're wanting to know the f of, and then you subtract off the x1. So that's how you take care of the linear part. So for the quadratic, we have that same b1. We have the same b2 that we had earlier. And this really defines what the b2 is, if you will, times x minus x1. So here we go. We're going to define a b3. So bracket 3 or b3, and that's going to be that is going to be in a almost like a recursive kind of way. We're going to call out an f, a b2 of x3 x2 and a b2 of x2 x1. So that's how it works. And this is like the slope, change the slope, if you remember. And you're going to divide by the endpoints of that segment. So the difference of the endpoints, so that's going to be x3 minus x1. And then you're going to be taking what you had earlier, and you're going to add another factor, an x minus x2 factor. So this is what you do. And I've kind of written it in terms of a bracket notation rather than the prime. In the bracket notation, this is the bracket. That's the definition of a two bracket, f2 of f of x2, x1. That's how I define it. And then I could just recall that right here within my f3 bracket, my b3 bracket, if you will. So it's going to be nested or recursive, calling the b2 brackets. And then again, dividing by the endpoints. Okay, so that's a quadratic. And then for a cubic, so I just repeated the quadratic so that you could see I've really got that same thing here. And I'm going to add in the cubic. So the cubic is going to take, and it's going to rely on the b3 up here. Got b1, I got b2, I got b3 based on the three element bracket there. And then kind of putting it all together, I'm going to end up calling out a b4 that relies on a b3 style bracket, the difference of them divided by x4 minus x1. So kind of how it works is the three element bracket is going to have x3, x2, and it's going to be minus x2, x1. If I look at the B4, it's going to go x4, x3, x2 minus x3, x2, x1. So you're kind of segregating the x's, shoving for the 4, you're looking at the 3 that are on one side, and then you have minus the 3 that were on the other, and you're dividing by the difference in the end x's. And then here I've got x1, x minus x1, x minus x2, just like I had here. And I'm going to add another factor is x minus x3. So that's the cubic, and that's what we're going to show you how to program right now. So there's the cubic. And if you look at my cubic interp function, so this is my MATLAB cubic interp, and we're going to show you the results of it. The x is coming in. That's my 75, and then I think that my indices were like 4, 5, 6, 7. So I had 4 indices into the x's. I think there were 4, 5, 6, 7. So the 4th x, the 5th x, the 6th and 7th x. That's what kk will be. And then I'm just going to use the KK1 as my first value, first one that I want. KK2 is going to be the second. KK3 is going to be the third. KK4 is going to be the fourth. So the first thing I do is I just go term by term here. I'm going to add in my B1. So that's going to be the Y. So my data is coming in as a bunch of X's, and my Y's are coming in as a bunch of Y's, Y data, XD, YD. So my YD is my F. So I'm going to pull out that very first one, and that's going to be my B1. And then I'm going to just add to it a BRAC2. So there's my BRAC2. So my BRAC2, I need to give it the F2, the F1, and then I need to give it the X2 and the X1. And then when you look at my BRAC2 function, really, I just give these to students because it's just trivial. They're so easy. So I've got F, F2, F of X2 minus F of X1. That's what I have there, F2, F1, subtracted. There's my numerator. Denominator, X2 minus X1. So the BRAC2 is just trivial. And I'm doing BRAC2 right there. You can see it. So I've got the Y's being my F's, 2, 1, 2, 1. And I'm going to multiply X minus XD. So that's the first X. So that's going to be giving me this factor right there. Right? So I've kind of have my first, my linear part taken care of. Now the next line, I'm going to add in my quadratic part. So for the quadratic part, that's going to be a BRAC3. So BRAC3, I've got F3, F2, F1, and I need the X's, right? So for that, I'm going to recursively call the lower BRAC. So I call BRAC2, F3, F2, X3, X2. So that's going to take care of, so I'm trying to take care of this bit right here. And then I'm going to be subtracting off the BRAC2 of where I'm looking at the other two, the F2, F1, X2, X1. Quantity, divide by the endpoints, X3 minus X1. So that's my BRAC3. And if you look, I've got that BRAC3 coming through. I give it to 3, 2, 1, 3, 2, 1 of the Y's or the F's, and then the X's. And the dot, dot, dot means I continue because I'm going to multiply by X minus X1, and then I'm going to multiply by X minus X2. That's what this is doing for me. So that takes care of the quadratic part. Now I'm going to add in the cubic part, which is a BRAC4. So slide over a little bit here maybe so you guys can see the BRAC4. So the BRAC4 depends on the difference of two BRAC3s, 4, 3, 2, 4, 3, 2, and then 3, 2, 1, 3, 2, 1. So just separating the 4 points into two groups of 3, and you have the difference, divide by the endpoints, X4 minus X1. So that's my BRAC4, goes all the way to there. I'm going to have the X minus X1 times the X minus X2 that I had previously, adding in that last factor, the X minus X3. And then I return Z. And that's how cubic interp works. Very straightforward how you build on these BRACs. And it makes it very nice. Don't even have to calculate the polynomial. You could if you wanted to, but this is really much easier than doing that. Okay, so here we go. So here's what I did, and I'll show you the code in a minute. So I took the blue, it's just the data. The blue is just going data point to data point, doing line segments. And when we zoom in, you'll see that the blue is very, very coarse and just kind of faceted line segments. And then I took that cubic that I created, with the cubic interp, and I did a very fine graph between my 4 data points. The diamonds are the data points, 50, 109, 100, 0.946, and etc. So the diamonds are my 4 data points. I did the cubic interp and then filled a nice smooth cubic amongst all 4 points, goes through all 4 points. And then I was interested in that 75, what that looked like and how it was configured. So the circle is the 75 that I was interested in. So we zoom in a little bit. You zoom in, you can see that the red is a nice smooth curve, and the blue, if I were to use like a linear interpolation, the circle would be a little bit higher up and it wouldn't be as nice a fit as the cubic, because if you look, the points that are coming later actually kind of curl to the left. If you had this view of here pointing and looking at what the points are doing, kind of bows it out, so that means that the circle is better where it is right now, considering how the points would fit in the future, rather than just doing an interpolation on the blue line as a linear. So the cubic has given us a better result here. Very nice. And here's how I did that graph here. I had my raw data, XD, YD, and my KK, as I was saying, was going, what was it? 1, 2, 3, 4, 5, 6, 7. So 4, 5, 6, 7, 4 through 7 sets up my indices into my X's and my Y's. And then I went ahead and got my YI from that XI being 75. And I think that was it, the XI YI. I did that as a circle in black. That's what the OK means. And then I wanted to do a fine. I wanted to go from 50 to 100, very fine. I think that means it by increments of 1. And I did a cubic interp of everything there, and that was the FI, YFI, XFI. So that's going to be the very fine one, and I did that in red, as I showed you earlier. And then the data, the raw data, I did that with a D diamond. The 4 data points, did those in diamonds, and then I did just the raw data in the blue kind of faceted course. So very, very straightforward how I did that plot and how I did the interpolation example here. Right. So that'll do it for today. Very nice. We were able to look at all that data just kind of coarsely. We picked out 4 data points. We fit a nice smooth cubic through there. We looked at one particular point, the 75. Okay. So hope you enjoyed it.